Okay, so we're going to spend time today talking about another, uh, as I mentioned before, there will be some mathematical manipulation that you need to know, and it will be useful later on studying electromagnetic theory, right? So I think it's going to benefit you from today's on until you're doing EM2 and everything else about the differential equation and all this stuff. All right, it will be pretty fun today. I don't know you call it fun or not, but we'll see. Okay, all right. So we're going to use the handout, the note number 7. All right, and what we are going to focus on today, only one thing only, and that is the divergence. All right, for those of you that has done Cal 3, yeah, I think. Okay, so we already saw the gradient function already, the gradient of a potential function, generating a vector that gives you the directions of the steepest change of that potential function or any scalar function. So now we have another operation that we're going to deal with that related to the word divergence. Oh, all right. Just the word alone is just saying something that is diverging out. So when you try to create something about this word, so it's probably going to say something about something is about to diverge out. All right. And then eventually we're going to define that. What does it mean by the divergence of a vector function? So the key is we're going to try to figure that out for a vector function. Of course, what are we going to use for? Of course, our vector function that we are focusing on right now is the electric field. So eventually we're going to come back to this electric field vector. However, because this is just any divergence, so it could be a divergence of any vector function. So I think we just jump off from the electric field and just talk about any vector field, any vector function. So let's call them F. Okay, all right. And then we're going to keep them in three-dimensional space. So that means we can explain this one in R, Y, and Z. All right. But a good thing about this one, though, make sure in your mind, we now have R, theta, and something that we are eventually we're going to get to it when we learn about some other coordinates that we're going to sort of like look at it in more detail later. So that means this allows you to express your vector function in any coordinates that you're supposed to sort of your preference or related to the problems on hand that you want to apply some different coordinates. It will work in pretty much the same way. All right. However, of course, by using different coordinates, you are introducing different geometry. So maybe the form of stuff might have to adjust accordingly, maybe. All right. But overall concept stays the same. All right. So first of all, what we're going to do is this. It's going to look familiar at first. So you have a finite volume. Okay, so everyone's still all right. It's like when we like start the video, started the lecture, we just like go right into it. Don't see our faces. So, all right, just sort of jump right into it. มันเรียนแบบนี้มันเข้มข้นดีนะ All right, okay. So feel free to ask questions along the way anytime. All right, just make sure you get what we are trying to get to. All right, so now we take a look at the finite volume of some shape. So that shape could be some arbitrary shape. All right, which now we can say that's that is a surface that we're gonna call them S. Yeah, sounds familiar. So we have a surface. This look like a balloon, and we have a surface right there. So what we did before, all right. So we were looking at the flux through this surface. So that means if you have a vector, any F, and then you want to look at how this vector is penetrating the surface. All you care about is figure out the flux through this whole surface. The way to do that, if you still remember this, so what you do was you sort of like slice this out into a tiny patch, and we say that that patch will have an area. So we call this area just a tiny bit of area. Let's call it dA. However, we introduced the vector form of this area. And we always say that the vectors of an area is always point perpendicular to the actual surface. Okay, so right, sort of remember that. All right, so that means we're gonna put a vector form of this dA. So let me highlight this one as a red vector right here. So that is your area vector, and it's perpendicular to that patch. All right, and we were discussing about pointing inward and pointing outward. And of course, we always take a look at the closed surface, right? Back in the day of the Gauss's law. So there's no doubt, we always pick the directions of this area vector to be pointing outward from the enclosed volume. Okay, perfect. So far so good. This one looks just exactly like Gauss's law that we did before. We try to calculate the flux through any surfaces. Exactly the same. So the net flux through this surface can be written like this equation. So all you need to do is just calculating the flux through that tiny surface first. So you say that tiny bit of flux, you can call it like the differential of the flux. And then all you need to do is just taking the component of the vector F that going through the surface in the perpendicular fashion. All right. However, because we already defined the area vector to be perpendicular to that surface, so all you need is just you take the component of the component of the F that is pointing in the same direction as the area vector dA. And the operation that allows you to do that is just the dot product. All right, cool. So far so good. All right, and then you want the whole flux through this. So all you need to do is just integrate them. And then you get the net flux through. Is F force? No, sorry. I was just it's run in my head. All right, so F could be any vector. It doesn't have to be force. It doesn't have to be anything. It can be velocity. It can be acceleration. It can be heat flux, heat flow, anything. Anything that you can represent it as a vector function. Okay, sorry. I was just let that force out. And it's just this association F with the force all the time. It's too deep in our memory. Okay, all right. So with that, that is your net flux through the surface S. So we probably call this as a surface integral, which is fine. No problem. Okay. Now, what we have to do next, though, this is what we want to do today. So far, so good. What we have been talking so far up to this point, this is exactly what we tried to establish Gauss's law back in, I don't remember the topic's number, but that's what it was here. Now let's try something. So what we try to have you imagine along is this. What about if I divide this balloon into two sections, upper and lower? Okay. So now that means your surface is being split into two surfaces. Let's name them S1, the upper surface, and the bottom one S2. And of course, the volume will be divided in half. I mean, it doesn't have to be in half. Divided into two volumes. Let's call them V sub 1 and V sub 2. All right. And right at the intersection, of course, you're going to generate a surface. Let's call that D for now, just to distinguish that is like a divider or something. The one that divide the upper volume and the lower volume, or slice this volume and then generate a new surfaces. There's an upper surfaces and a lower surfaces. Okay, looks good. Now, my question is, if you try to do the flux calculation, okay, but now with an extended surfaces. The reason I say extended because you have that extra D surfaces. When I say surfaces, because you have both sides, right? Just the D alone is not a closed surface. It's just a flat surface. So you have two sides of the D. Okay, so what about if you try to do the flux calculation throughout these two surfaces, S sub 1 and S sub 2? What do you think it will happen? Whoa. Do you think it's going to get the same stuff that you had before? My question is it going to be still that flux, just like you calculated from a single surface around the balloon? The answer is yes. Can you see why? When you look at this. Okay, so every time that you are looking at vector going through the surface, all right, so it seems like the calculation on the upper portion of the S1 surface, it seems to be exactly the same as before. Same thing with the bottom. It shouldn't have anything different. The only things that are going to show up and then do some funny business here is just on the surface D, right? The one that you just generate due to that cutting. However, because of the D, it is an open surface. Okay, let me highlight this one. The D itself is an open surface. So what it means is, okay, let me have one single vector going through here. And let's say it cuts that D right on. I mean, it just penetrates through the D. When you say penetrating, so if you look at the upper side of the D, the area vector is pointing in one direction. It's pointing outward, right? So let me call this DA. But when you look at the bottom of this one, the area vector will also point outward. But now it's going to be outward toward the bottom side. You guys with me? It's an open surface, right? So when it's open surface, when you look at this side, the area vector will point out. If you look at this side, the area vector will point out that way. It's pointing out. Because this one, you have two choices. Yeah, nothing you can do. It's not a closed surface or anything. So for this, that means if there is a vector F trying to get through a point on the D, the surface, D surface, that means one gonna have the angle less than less than 90 degree. However, on the other side, you're gonna go opposite direction right here. Do you see what I'm saying here? Okay, or if you think just, you don't have to worry about the theta. If you think of this open surface D, when you are looking at a function, the vector function F penetrating to a point, there will be one that you can say is an incoming, right? Think of it like there is an incoming on this side and it's gonna outgoing on the other side. However, no matter how much you get in, it's gonna get through it to the other side. So in, there's one sign, out is another sign. So it means when you do the dot products to try to get to the flux, the upper portion will give you the positive net product, and the bottom one will give you the net negative product. So at the end, they will cancel each other out. อันนี้อาจารย์พูดยาวไปไหม But you see what I'm saying here is every time you try to cut the volume that started out so clean, there's nothing in there, it's just a closed volume. And then you try to cut them, you generate a new surface at the plane of the cutting. At that plane of the cutting, no matter the vector is going through, one side it will be inward, and inward, I mean, from the perspective of that cutting surface. So that will be in, and it's going to go out on the other side right away. So these two will be exactly the same magnitude, and it's one is in, one is out. So they always cancel each other. So no matter what you're trying to calculate the flux on this D surface, you're always going to get zero. งี้คนทันไหมเข้าใจไอเดียเนาะ Alright, so at the end, the overall effect will still be just an outer surface. Just only the flux on the outer surface that's going to give you a non-zero contribution. Oh, it doesn't have, it could be zero, but I mean, it will be just the outer surface that contributes to the net flux on this whole surface. How is it coming out? What does it mean coming out from where? Have to ask. Is D like a cross section? No, D is like, yeah, you can think of it that way. If you sort of slice them nicely, like cut straight out, you can think of it like a cross section, yeah. But it doesn't have to be a straight surface. You could do any curvy stuff, whatever you like, yeah. Yeah, but if you do it straight cut, then you're gonna get like a cross section like. So how is it coming out from the surface? Coming out from a surface. Okay, what we are doing actually is not, it might not be coming in or coming out, but because you are looking at a point. Okay, let me highlight this point right here. So at this point, you will have a function f defined at a point. Yeah, there's no doubt. But when you have this point analyzed, there will be an upper side of this surface and the lower side of this surface. The upper side, you will have the area vector point upward. The bottom side, or the other side of the plane, you'll have the area vector pointing downward. But you are still analyzing the same F. So if you look on the top portion of this one, then you say that the F and the dA are seems to going in the, less than 90 degrees, so they are pointing along the same direction. When you look at the bottom side over here, when you look at the F and the dA, they seem to go in a different direction. F is trying to go up, dA is trying to go down. So we know from the dot product, when you have the dot product, when the theta is less than 90 degrees, you get a positive dot product. If you have the theta larger than 90 degrees, you get a negative dot product. However, these two are exactly the same. It's the same area, it's the same F. The only thing is just the different direction of the dA. So they are canceling each other out. Make sense, bao? Yeah. Okay, very good, very good. พอได้อยู่นะ All right, so I can keep doing this. When I say keep doing this means I'm gonna slice them even more. Seriously, not only two. Yeah, I kind of get it. Okay, all right. So what we are doing is we're gonna slice, cut them like crazily cut until you're gonna generate like crazily larger numbers of this. There's so many D's now, that cross section that you were talking about. And we all know, no matter what you're trying to do the integral, at the end, the only thing that is going to contribute to the final result is going to be just the outer surface. The newly generated surface inside, due to those cross section or the cross cutting or whatever, the slicing, whatever, eventually will give you perfect cancellation anytime. Yes? Looks good? All right. So that makes it so cool that, yeah, we can keep slicing as small as you want, as many volume as you like. You can do like crazy. Those summation of those numbers of slices that you're gonna give you back the same amount of flux that you generated from just a single balloon surface. All right. So you guys probably start to wonder, why do we have to do this? Because we have been fine just looking at just the outer surface, and we already accomplished the Gauss's law and the Gaussian surface. Everything looks nice and clean. Now you just suddenly decided to slide this whole thing and then try to show that if you try to calculate the flux through all these crazily created surfaces, you still get the amount of flux to be the same anyway. So what's the point? The point is this. Okay. Now, when you try to increase the number of slices, or you can think of it like a number volume. So each tiny portion of this that you get, you can think of it like you're going to generate like a tiny volume every time. There's a mini volume around the point of cutting. And then when you cut so many, so each portion of this one will take up some volume near them somehow. There is like a tiny volume every time that you do the slice, crazy. So if you have the n to be super big, so take the limit of n go to infinite. All right, so that means you can shrink down the surface into like a super tiny. Okay, and then it seems like every time you double the n, so you seem to sort of like, hey, I'm gonna have more integral. Okay, so it's gonna double the number of integral. However, the value of integral individually is supposed to be smaller in half from the look of it, because by this interpolation, it means that no matter what you try to manipulate, you're cutting, the result is fixed to be flux phi. So there is something about the amount of flux that coming out at that tiny volume. But when you get more cuts, for example, like I said right now, you double this volume, so the volume of each one is going to be less. All right, so that means that amount of flux supposed to somehow compensate for that to make the net flux constant at all time. Okay, all right, so it seems like there is some relationship between the surface integral. Okay, the surface integral, this is the one that we did over here. Yeah, let me highlight just a little bit here. Surface integral, there you go, bam. Okay, that F and the dA. Okay, let me color coded the dA a bit. There is that flux calculation on the surface and the underlying volume near that point of calculation right there. Seems to get something here. Okay, so there was a reason why we tried to do that cutting, because it seems like there is some relationship between those surface integral and the volume that's accompanied that cut, and that is the one that we are interested in. Okay, so in each particular that subdivided region of your balloon, we are now interested in this, the surface integral over volume. All right, okay, looks good. Keep going. All right, it might still like cloudy at this point, but it's gonna emerge, it's gonna diverge out in a bit. All right, get going. So when n is large enough, okay, like I said, it's gonna get like go crazy. You can keep increasing until things go to infinitely many amount of subdivided volume. So that means when you take the volume to be super small, which is equivalent to n going to infinity, so that what you want is you want to take the limit. Okay, let's staring at this expression a bit. So when you take n to be huge, that means the volume of each one will get so small. So it's small. Oh, y is in the denominator. So because we are interested in this. So we want to do the relationship between the surface integral and the volume that accompany that surface. So we would like to take a look at this ratio. Okay, we want to know what is going on per unit volume. That's what our point is trying to get to. Okay, make sense? All right, that's no, it's just something interesting, let's say. Right, but there's no derivation of this. It's just, hey, let's take a look at this surface integral over volume and see how it goes. Sounds nice? Okay, all right, very good. So what you have right here is you would like to take the limit to be super small, and then you still would like to try to calculate the surface integral on those stuff. And then if you take this limit, okay, we're gonna call this the divergence of that function. This is by definition. Okay, you probably like, Ajahn, so what is the conclusion right here? The conclusion is this. So we're gonna try to extend the concept of the flux one step further. We are trying to get the flux just like before, but now we imagine like this flux is coming out from a volume. Make sense? Okay, one more time. Before, we assume that there is some electric field vector. So we assume that there is already a vector field that can be represented as a vector function. And once you generate some surfaces, you can calculate the flux through the surfaces, no problem. That is just a surface integral. But now what we are trying to do is we're going to extend that idea of flux calculation further by looking at this and the slicing that we did up until now. Eventually going to give you a tiny volume that is attached to that surface integral every time that you try to calculate that flux. So you are trying to think of the flux per unit volume. With me? And that quantity, we name it divergence of the function ครับผม ถามเลยครับ all right you can turn on the mic if you want I mean if you don't want to type oh okay are we doing divergence of magnetic or electric oh so far at this point is anything because we define f as any vector function so this one works for any vector function right you can do with electric field you can do with magnetic field works the same way okay all right so this is the extension that we got and this extension we name it the divergence of f and then we use the symbol div to represent the divergence of that vector function f okay very nice so far so good all right so and of course there is like a pre-assumption that the integral is supposed to exist everything the limit supposed to be converging to some number on and on so we always assume that all right we're not going to try to deal with the vector function that give you a divergence result okay all right well I'll keep saying divergence diverge the limit supposed to converge not diverge but it just accidentally we're talking about the divergence of a function so it's sort of using the same words or something okay all right here we go now what is so cool about this one บอกอาจารย์ like why don't we just be content with what we had with the flux calculation and the surface integral why do we have to deal with the flux per volume all right and this is what's happening so when you're trying to do okay what we are trying to get to is this so if we go backward starting from the divergence of f okay so what we have at this point okay let me summarize so what we have over here is this so if you want to go back to what we had before in the Gauss's law all we want just doing this surface integral right okay but the idea of this is we just say okay we can slice this into many surfaces and the sum stays pretty much the same and then we can re-express this whole thing now to do like it's like you think of it like I divided by v sub I multiplied by v sub I and then sum the whole thing up so everything stays the same and now we're going to take the limit right so when I take the limit this whole thing right here we're going to name them divergence of f in the limit of n going to infinity or v approaching 0 okay so everyone see this is a whole summary of what we have been doing okay we start from the flux calculation we can slice them any way you like the volume the newly created surfaces won't contribute anything new to the flux calculation but then we're going to do the flux per unit volume so you can think of it like you multiply by the v sub I and then divide it out so you're not doing anything and then when in the limit of n approaching infinity so everything go in the name of divergence of f but of course when the v sub I approaching 0 what do you see this going to 0 the summation go to infinity this turn into an integral so actually I can re-express this term okay let me write it down here like an integral of the divergence of f and that thing that going so small let me name it the dv with me so that's what you get right here I let you stare at this for a moment all right so for those of you that familiar with the well I don't know you're familiar with this right because when you were introduced the divergence for some of you that already taken the calculus 3 you might have not seen this kind of derivation anyway so you just jump right into how to calculate the divergence so what we are doing right here overall just from this line alone it looks just like you're starting from a flux calculation and then you try to hey let me re-express this whole thing in terms of the flux per unit volume or something like that and seems like that concept is already worked perfectly with the mathematics, vector calculus, and names divergence of a vector function. So with that in mind, I can re-express the flux calculation which related to the original function alone. I can turn this into a divergence of f that linked to the volume, guys. This is it. One more time. This original integral, the flux calculation, that was surface integral. When it's a surface integral, it means this is just, you can think of it like it is a two-dimensional integral. It's an integration over a surface. With the help of this definition of the divergence of the function, f, if you turn that f into the divergence of f, then you can turn your integral into a volume integration. This is triple integral. Think of it that way. And this is just a double. Isn't that cool? What it means is now, back in the day, this one, you look at the f as function, vector function, and then you try to calculate the flux from a surface that you built right here. You have to come up with a surface, and you look at how this vector gonna penetrate through your surface. Yeah, that's what we did before. But then by the introduction of the divergence of the f, so it turns out right here, same place, same spot, I can also calculate divergence of this f at the same spot right here. And this actually give me the information about the f inside this volume. You guys with me? So it seems like that is another way to look at the characteristic of the f. Instead of looking at the f alone or directly, you calculate the divergence of f, and then you somehow associate this divergence of f into a tiny volume that this f is standing. So that's why it's equivalent between doing the f around a surface, or you want to do the divergence of f on the volume. Whoa, you can do this, you can do that, you can do it here, you can do the volume there, you can do a volume here. So you just keep doing the divergence of f around the volume. Bop, bop, bop. You keep summing them. At the end, the result will be exactly the same as when you did f on the surface. So now you have two choices. You can look at the f, the original vector, and you do the surface integral, get the outer surface, get it done. Or now, you can say, hey, let me grab the divergence of that f, and I am going to do the integral for the entire volume of this whole thing. I'm going to get the same result. This is intentionally silenced. Intentionally quiet. Okay, you guys still with me? All right, so what we have at this point is now with the divergence of f, that allow you to calculate something about f, right? But under the volume instead of surface. That sometimes make it nice because, okay, now here's the cool thing. Look at the Gauss's law. Now let's turn our attention back to electric field. So now I'm gonna pick f to be E. So in the Gauss's law, remember we did this, right? The integral of E around any closed surface will be equal to, let me write it, Q over epsilon naught. Okay. And the Q is supposed to be Q inside, of course, right, all the time. However, you can also calculate the Q from the density. Yeah, the density of that charge. And we already did this many times. Okay. So in the three-dimensional space, you take the density charge per volume multiply by the volume, and then you do the integral over the entire volume. You get back the amount of charge. Okay, sounds cool? All right, so there's a question comes in. When we do divergent F, do we do all sides of the small volume? Well, the volume is so small that you just need to consider the divergence at the point. With me? All right, so we'll have some discussion later about that. But it's like, you think of it like this tiny volume is small enough. Everything's shrink down to 0 already. So you can just specify a point in the middle. Think of it that way. And then you just find divergence of the vector F at this point and use that as a representative of the whole dV, the tiny box right here. Okay, so you don't have to worry too much about which side, or it's like the upper side or the lower side. There will be some variation, but once you try to set the limit to 0, everything will shrink down and everything just works perfectly. Okay, all right, but that's a good question actually, because that is something that we are about to discuss a little bit later, maybe after the break. Yeah. All right, but keep that in mind. Okay, here we go. So from the Gauss's law, the left-hand side, that's just a total flux through the closed surface. The right-hand side is just the charge per epsilon naught. But when you look at this one, hey, Dan, on the right is a volume integral. See something now? So I'm going to use that relationship on top, re-express this equation in this form. Why not? So now instead of looking at the E, and I have to do that dot with the dA, do the integral over the surface, I calculate the divergence of E. And within that same surface that I'm doing, I'm going to do this integral over that entire volume of that closed surface. And do you see something here? Now, this is also a triple integral. It's a volume integral. So that means whatever inside is supposed to be the same. Yeah. Because we started everything from the same flux calculation. And that draw you to the conclusion. Whoa! The divergence of electric field equal to the charge density divided by epsilon naught. This is a wow moment, guys. All right. And mathematically, whatever you just saw on top, this expression right here, that's named Gauss's theorem or divergence theorem. All right. Some of you might have already seen this from Calculus 3, but for those of you that haven't done those, that's okay. This is just the relationship between the vector function f and the divergence of that function. But the key is, on the left is a double integral, surface integral. On the right is the volume integral. And once you utilize this in our Gauss's law for electric field, it turns out I can re-express everything in terms of the volume integral, and I just match whatever inside the integral. And I just said, hey guys, the divergence of electric field equal to the charge over epsilon naught. What do you think about this? Well, all that makes sense. Because we already sort of tried to think about this from Gauss's law, that the charge is the source of the field. Wherever you have the electric field, there must be a charge generating that field. All right. And then what you had done before was just you try to get to a clue from wrapping that charge somehow and looking at the electric field that tried to leaking out from your enclosed surface. Yeah, that's what we're trying to do. We like sort of like build up a balloon and looking at what are the electric field lines that piercing through the balloon surface. And then you try to count those, calculate flux. Now, there is another way to look at it. So now you have electric field coming out. All you need to do is just, okay, I'm just going to look at the characteristic of this field. And that characteristic that I'm looking at is the divergence of these fields. If I can get to this, it will be an indicator that there must be some electric charge in there, in that volume right there. Okay. Oh, there was a question. What is charge per epsilon naught? Okay, so this one came from Gauss's law. So remember that. So back in the Gauss's law topics, we say that every time we do the flux through an enclosed surface, okay, the amount of flux that you get must be equal to the charge inside divided by epsilon naught. That was the Gauss's law. That was the relationship between the electric fields coming out from any charges generating the fields. And now we have another way to look at the Gauss's law. We say the divergence of the fields directly tell you the charge density. Whoa. And this is also the Gauss's law, but now we say it's in a differential form, not an integral form. So every time you type in like Gauss's law or Maxwell equation, you have two choices. You have the first choice to be in an integral form. It will look like this. Or you can have a differential form that looks like divergence E equal to rho over epsilon naught. That's kind of cool. Wow, this take longer than I thought. Alright, พอใจไหมพอได้อะไรบ้างไหมเนี่ย What is EDA? EDA is the flux of the electric field vector through surface dA. EDA is flux. So total flux is this. So is divergence theorem more efficient than Gauss's law, or are they equivalent? They are exactly equivalent. Correct. They are the same. It's just the matter of when and where, which approach or which perspective is more appropriate for your setup. For example, from what we have done before, like you try to use the Gauss's law to calculate electric field from a line of charge or like a chart sheet on and on. Yeah, doing the double integral looks fine, right? I mean, just calculate like build up a Gaussian surface, calculate the flux through those surfaces, you get the electric field, works perfectly. And that will be like a tough business to try to get to the field first and then try to find the divergence of it. Okay. Still hard to visualize. Yeah, I know. Both of them are kind of like, you have to get some time and then, you know, get used to this stuff. You have some kind of animation. Yeah, maybe. But before to get to the animation, we will have some other stuff to show you. Yeah, it's interesting. It might not be a visualization just yet, but it will be something that will give you some idea what does it mean by this divergence of a vector. Sounds good? All right, so why don't we take a break right here? I think have you guys sort of think about this and let it sit and sort of crystallize a bit. And then after the break, I will try to answer that, try to visualize a little bit more by using this variation of the actual field. And this will go back to answer Nan's question a little bit about, do you have to worry about what's going on top, on the bottom, on the side? What about the, you know, the surface of the stuff that we sort of break it out? Yeah, I think this will answer those two questions. Sounds good? All right, so after coming back, I will explain what this divergence is about in more detail. Okay, for now, just think of it like a definition, sort of. All right, so let's take a 15 minutes break and then we'll come back and explain a little bit more. Okay, sounds good? All right. Welcome back. All right, I don't know, you guys, probably confusing at many parts. So what we have to do next is probably I'm going to sort of go through a little bit more. However, because some of you asked about visualization, and I think I got something to show you. So what about I'll give it a try. I'm not sure if this is going to work, but might give you something. So just allow me to try. Okay. All right. So there is a, I don't know what kind of plotting software that you guys use most of the time. Okay, let me stop sharing from this, and then I'm gonna have something else to share. Okay, give me 1 second here. There you go. All right, so I'm going to share the screen, which is, I think is right here. There. Alrighty. Okay, you see that? I hope I'm trying to look at it as well. Okay, so let me sort of make it bigger to make it fit the whole thing. That might work. Okay, you guys see this? All right. Okay. I'm confused. All right. Anyway, I'll just keep talking. Just let me know if there is anything comes out. Okay. So this is the Cal3 plot is a web plotting software that I mean, I'm not an expert using this one, but it seems like it's easy enough to do some simple plotting program. So what you can do is actually, if you look at this program right here, you have an ability to try to plot a function. I think this is very good. So I use this when I'm doing the calculus 2 or 3 or something, when you have the vector calculus courses, and then this one helps a lot. Like you can draw like a space curve, like a parametric equation curve, and this is the one that I'm going to try, the vector field. You can pick a point in space, you can draw a vector, you can do some parametric surface, and then there will be like a slider cutting. It's pretty good. All right, so in terms of like a web plotting software that you don't need to know how to learn the language a bit, like Mathematica or something like that. Okay, so what I'm having for you guys here is, okay, let me eliminate this. Okay, so what I have is I just select the vector field. Okay, so from what we have over here, I'm gonna try to do something simple, and I'm gonna give you this. So if I write like 1 and nothing else, so I assume from this software M, N, and P give you the member of your coordinates. Like if I'm using like rectangular array right here, M, N, and P will represent X, Y, and Z components of the vector field. So with that in mind, I can do the plotting. Bam, this is what you get. All right, cool. So I'm just drawing one layer of this because I specify that I use just along the Z-axis, I use only one number of vectors. But actually, I can make this like a 3D. So if I remove the restrict view, so I get a 3-dimensional plot of this vector space. See that? Okay, I can change some angle slowly. It doesn't really go slowly. I don't know, in the zoom, it might jerky a bit. Okay, here we go. So this vector is easy. I say that in the X direction, I have the vector of the size 1 pointing in the X direction. So that's why I don't have any other components of the vector. Y is 0, Z is 0. So no matter where you are on the XY plane, you're going to have the vector pointing along the X axis have the size of 1. You guys with me with this? Cool. So if I'm going to give, like, let's say I give it 5. So that will give me like an plotting of this vector space along the Z axis as well. And this will allow you to see sort of like a 3-dimensional stuff now. So these are the vector field that I draw, like 5 layers of this stuff. I let it rotate. It might be very jerky on on Zoom, but okay, let me move things around a bit. Here we go. All right, so let me find a good angle here. There you go. I think this is okay. See, so I just draw 5 layers of these vector fields. So that's what it is. It's just a field of vectors. So instead of having just like a function, scalar function, when you pick a point X, Y, Z, you will be able to specify the vector at that point, X, Y, and Z. Okay? All right, just to sort of like show you a little bit, this is like a constant field. No matter where you are, you have a vector of length 1 pointing to in your x positive x direction. So let me do like a variation. So if I put x in here, so now what you are getting is going to be something that is changing. I think it's plotting. Here we go. So what you have over here, okay, let me remove, okay, let me restrict to 2D. Here we go. So what you have over here is you're going to have a dependence on x. So that means you still have the vector that point along the x-axis. You still don't have the y component. You still don't have the z components. However, when I write this function to be depending on x, so the further away or the bigger the value of the x, you get a longer vector. So that's why when you move toward your right side of your x-axis, the vector length is longer. And of course, you're going to get a negative one because when you move to the negative x, you have a negative of the vector, though it's point in the opposite direction. It's cool. A bit. Now, answer your question. So just to make things a little bit easier to see, I am here. There is an option in the bottom where my mouse is right now. The objects add to the clicked point, I can pick to show you a flow line, a curl at point. Curl we haven't studied yet, but that will be your third techniques that we're going to learn in the course. But now what we are doing today is a divergence at point. So what I'm going to choose is I'm going to choose a divergence. And I'm going to pick a point here. Bam. You see this? Yes? So this is what's happening. You might not be able to see it clearly. So what I can do is I can have this more. Let's do it like a very frequent plots. So I do it like 15 times. Here we go. So I just sort of draw this more frequent for each point. I mean, pick 15 points along the x-axis. I'm going to plot these vectors. And I'm going to click on it. Bam. So this is just a tiny volume of the, right now is 2-dimensional. So it's an area. But when you zoom into this, wham, 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 oh, I try to get there. Wham, 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 wham. Okay. So let me take out the restrict view. Here we go. So when you look at this, so let me turn this back in the XY direction. And if I zoom it in, wham, 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 wham. Okay. So can you see this? All right. Because there is an electric field. หลายคนคงงงอาจารย์ทำไมไม่พลิกทางฝั่ง positive Okay, let me do a positive side. Sorry. Okay, let me pick here. Okay, here we go. So if I pick on this, okay, and if I move thing point around, okay, this is the divergence at the point of my click. With me? Because when you look at this one, okay, I don't know if I can get to that. I try to get to this. Okay, so you see that the vector field on the left side of this is quite small. The vector field on the right side is going to grow bigger because of the x dependence of this field. So when you look at just around this circle alone, the left side of the circle will have the incoming vector. The right side of the circle, there will be an outgoing vector. But the incoming vector is going to be a little bit smaller than the outgoing vector. With me? So the net of the flux, right? Because when you want to calculate how much is in, you take the vector and do the dot product with the surface. How you want to know how much vector is out, you take this vector and dot with the surface. But because if you pick like a symmetric surface, like a box or a circle or something, the surface on the left and the surface on the right will look exactly the same. However, the magnitude of the vector on the left is smaller. The vector on the right is bigger. So the inward flux is less than an outward flux. So if you want to calculate the net flux within this volume or within this surface, you're going to have a net out flux. ช่วยปะวะ Yeah. So by looking at this and my explanation right now, I am talking about just the vector and the surface. I have to do the surface integral. I have to take the surface on the left, dot it with the surface on the left. I have to take the vector on the right, dot it with the surface on the right, and I do the net result to find out what will be my net flux. Okay? But now you're about to see, I can get you to the same meaning that the net is the outward flux by talking about the divergence at this point right here where my mouse is. Around this circle right here, the divergence is going to be positive. Why? Because something is outflow from this volume on this surface right here. So instead of have to go through the vector dot with the surface vector, all I can do is just evaluate the divergence of the vector field at a point. And I can tell you right away, if I pick this point, it will be a net outward flow of the electric field around that volume. I don't know, is that better or not? But okay, just have this visualization in mind. I hope it might help a bit. We'll see. All right, so we can turn this two-dimensional into a three-dimensional stuff. So you probably have to draw like a box or something and then try to calculate the net flux. And that's what I'm about to do right now. Seriously. Okay, I'm going to stop sharing here and then I'm going to go back to my slide. All right, 3D cooler better. Cooler better. What do you mean cooler better? It's way cooler. Okay. All right. So let's continue. All right. Now this is exactly what I am about to do. I have the vector field F. Okay, you guys slowly sort of move along with me here. I am picking a volume. There you go. Everything is in the Cartesian coordinates, dx, dy, dz, the width, the length, the height, no problem. I am about to do the flux calculation within this box. Sounds good? All right, so this will answer, I think, Nan's question, I guess. All right, about what about, do we have to worry about the flux to the top, the bottom, the left, the right? Yes, this is what we are trying to do. All right, and it's gonna go crazy a bit. So sort of move along with me here. So I have some blank space for you guys to fill in, so you have like a chance to interact with the handout. Okay, first of all, this is the field. This is the tiny box that we are looking at. Okay, so when I blow up that portion of the box, so let's say the lower left corner right here, specify a point x, y, z. All right, not a problem. Okay, so because you know the width, the length, the height of the box, so toward along the x, so this corner right here will be x plus delta x, keeping the y and the z the same, something like this. All right, so you can extend in the x direction, you can extend along the y direction. So that corner right there will be just the extension along the y, so it will be y plus a little bit of the change along the y. And then you can go up if you want. So the upper corner right here will give you the x, the y, and then only the z that is changing. Something like so. Okay, yeah, something like that. All right, but anyway, the point is, what you really want to do is try to calculate the net flux around this box. Okay, so what are you going to do? Let's give it a shot. Okay, we would like to calculate the flux through this box. So let's move on to the next page. But before we before we get to that, well, Ajahn, if we have to calculate like 4 corners of this thing, it will be crazy. And at the end, eventually, you're gonna shrink this box down to 0. I know, because you're gonna go like everything like infinitesimal is small. So what usually we can do is just looking at the center of each surface of this box. So you can just go right ahead, pick the center. Why not? Right? You're gonna move to the left, you're gonna move to the right. Why don't you use just the areas in the middle? The result will be pretty much the same anyway. Okay, so what we're going to look at is just, let's say, at the center of this cube, this box right here. So if you pick the center of the box to be the point of interest, and then we try to calculate the flux, of course, there will be total of 6 surfaces that you have to calculate the flux. Start off, you're going to have to worry about what is going on the top of the box, and you can do the opposite ends of this one. So that would be the top and the bottom. And after that, then you're going to have to do the front and the back, the opposite surfaces. And then there will be one more left, the left and the right, on and on. Okay? So these are the exact same question you did back in freshman physics, probably, calculating the flux through a cube or something. Same thing. But now we're going to do it in an infinitesimally small box. Okay, here we go. Next page. So first of all, let's start from the z components. That means what I'm going to do is I would like to talk about the, here we go, let me highlight blue. So I'm going to talk about the surface on the top and the surface in the bottom of the box. There you go. These are the two. Okay? So first thing first, you should be able to note right away that the upper surface area has the area vector pointing up. So let me write it like this. You guys with me? Yeah, because the area vectors always point perpendicular to the box. I'm sorry, to the surface. Because right now the upper surface of the box is pointing up. So you say, okay, the size of the surface is going to be the width times the height, the width times the length, delta x, delta y, and it's pointing up. So you put the c hat into it just to say it's pointing up. What about the bottom? So same thing. But because we have a closed surface, the area vector is pointing downward. How much? Of course, it's still the same size, delta x, delta y, but now it's going to point downward. So you put negative z hat into it. So that's your area vector of upper and lower surfaces. Okay, fine. What else can we do? All right, what we want to do is we want to calculate the flux. So you have to know what is the value of the F right here. Okay, what is the value of the flux right here? But then, Ajan, we have the X, Y, Z waiting for you at the lower left corner. Don't forget, this is the field. There will be a vector waiting for you here. Let me write like a super big vector right there. Bam. That's your F. Yeah, at this point, right? Oh, that's a question. Sorry, I didn't see. All right, what's the question? Sorry, how you get the z delta x delta y? Okay, the z delta x delta y. Okay, it comes from here. So let me erase this one for now. So the area of this one is gonna be here. That's delta x. That's delta y. So now you know the surface area is delta x delta y. Width times length. And then you know that it's gonna point up. So you multiply by the z hats. Cool. Already? All right. So now, so don't forget, let's come back to our point. Right now, you have an electric, oops, sorry. You have an electric, you have vector field. So at that point, x, y, z, you probably have some vector f waiting for you at x, y, and z. I write it so big just to emphasize that that is the vector that you are interested in. So instead of, not instead, what you're trying to do is you try to figure out what is the vector at the x, a little bit, x and a little bit, y and a little bit, and z a little bit. So what you want is, I want to figure out the vector f at this red dot right here, which you already translate along the x by half of the delta x that's in the middle of the width, half of the delta y, that's in the middle of the length, and then you have to translate up by delta z, that's why it's up here. You guys with me? Okay, okay. So that means, let me call this F1, I mean, just for now. So that means your F1, which is F on the top. In the Z components, of course, because we care only the Z components. Why? Eventually, what you need is you're gonna have to break these components, and you only care about the F1 in the Z direction. You guys with me? Because now you know your surface vector is pointing up. So the only flux that will give you the full amount of flux is just gonna be the F at that point that is pointing along the Z direction. The X component and the Y component will have no penetration to the surface, so you get no flux. Okay, okay? So the only Z components of the F sub 1 will contribute to the flux through the top surface. How much is this? Ooh, what is the F1 in the Z direction? บอกอาจารย์ you can start from F at X, Y, Z. เอานะ ค่อยๆดูนะ so that means I'm starting from this initial point X, Y, Z. And then I use calculus here. I just want to move this value up a bit. Well, hey, don't go so far. I'm just going to move up a bit. So I just add, okay, dfz by dx. See, I just want to find the change of this f sub z component in the x direction. So it's a partial derivative of f in the x direction, df by dx. How far do I want to move? I want to move up half the delta x. Right there. Cool. นี่พอได้ไหมอันนี้อาจจะเหนื่อยหน่อยนะแต่ this is what it is. That's blue, not good. Let's use some other color. There you go. That's your pink right there. Okay. And then you're going to continue and do the same thing. All right, but wait. There will be a little bit of change along the y direction. Of course, that tiny change is this much. df by dy. How far you want to go from the x, y, z? Half the y. Delta y over 2. Same thing with the z. The last component, df by dz, everything is already in z components. And how far do I want to move? I want to move up by delta z. So let me color code it here a bit. So I want to move up delta y over 2. So this is how much do I need to adjust my original f at x, y, z. And delta z right there. Got it? Okay, so this is, you can think of it like a linear interpolation. Same thing. It's more like extrapolation. So you start from a one point and then you want to approximate what is going on when you go a little bit from that point by knowing the slope. However, this is the change in the three-dimensional. So you have to do it one direction at a time. So you're starting from your initial point. Well, hey, I'm starting here. That's my x, y, z starting point. And I want to extrapolate to this point right here, my red point. So I'm just going to have to move a little bit, knowing the slope along the x multiplied by the change along the x. Knowing the slope along the y multiplied by the change along the y. Knowing the slope along the z multiplied by the change along the z. That will give me the f sub 1. Oh, yeah. All right, but almost done. The reason it's almost done because here, try again. Let's look at the bottom surface. Let me name this f sub 2. But I'm going to use the same trick right here. F2, of course, because your lower surface pointing has a vector pointing downward. So the only thing that's going to contribute to this one is going to be the z components of my f sub 2. Cool. And we already knew the trick. I'm gonna starting from the same, that orange point right here, X, Y, Z. Okay, so let me write color coded here, F, Z, X, Y, Z. That's nice. Same starting point. Okay, let me highlight this one as the orange color. And then what do? How can you get to the blue spot right here? You extrapolate from the orange to the blue. But the good thing about this one is you only extrapolate along the X and Y. You still keep the Z level the same, right? The bottom surface doesn't move up in Z direction. So that's good. So that means the value at the blue point is gonna be just the slope along the X direction, and then you move half the delta X. Nice. And then you do the same thing with the Y direction. You move by half of the delta Y. Nothing needs to be done along the Z. Cool. All right. Now, once you get this, all you need to do is just doing the dot products. Okay. What about the flux on the top surface? Can you answer me now? ไม่รู้ตอนนี้ทุกคนไปไหนแล้ว You guys still with me? I already evaluated the f sub 1, which is the vector that is pointing, that's located on the top surface of the box. I only care about the z component of it. And I'm asking you how much flux on this surface. บอก อาจารย์ this easy now. I just take this, multiply by the dA. That's the flux on the top portion of the box, right? Okay, na. Okay, so what I'm doing is just I take the f sub 1 in the z component, multiply by the x, delta x, delta y. They're already pointing in the same direction. Perfect. So the next page is going to be quite long, but it's going to be simple. So I'm going to take that whole thing right here. The whole thing. I should be able to copy this. I don't know. I haven't done it before. I mean, never success. All right, here we go. No, that's not good. I don't know. I don't know the mechanism of this. All right, so what I'm doing is I'm going to take the whole thing. Oh, shoot. What's going on here? What's going on here? I made some mistake here now. Okay. All right, here we go. So I'm going to start with the F. Okay. It's going to be long a bit, but okay. Let me color code it here properly. So it's going to be F, okay, Z at X, Y, Z. That's your starting term right there in orange, followed by a little bit of change along the X, delta X over 2, a little bit of the change along the Y, delta Y over 2, a little bit of change along the Z times delta Z, and everything is already on the Z component of the F. There. This is the function at the top of the box. I multiply by the surface, delta X, delta Y. The whole thing just for this. Wow, it takes us like half an hour. Okay, that is just the flux on the top portion of the box. What about the flux in the bottom? But whoa, อาจารย์ the F's at point 2, F2, F sub 2 at the blue dot is pointing upward, but your surface is pointing downward. So you're going to get a negative flux. So you can think of it like there is the entering flux or influx from the bottom surface and an outflux on the top surface. Okay? There's a question here, why do we multiply by the change and not plus? Which portion? Multiply by the change, not plus. Oh, okay. You mean like single term here, why do we multiply, not add, right? Is that what you're asking? Oh, okay. So the point is, this term right here, this is the slope. Okay? So when you have the slope, then you have to multiply by some value to get back to the value. You don't add Because if you look at the units alone, that's bad. The slope has no units. So if you have something has no units, you add with something with the unit like length in meter, then you don't have problem. Make sense? Or, okay, for those of you that are confused, what I'm doing over here, this is the linear interpolation or extrapolation. If you have a point, you want to shoot this point to another point, okay? So you're starting from the original point xy, and you know that the blue point is delta x away. How can you figure out the value of the blue point? The way that you do is, you just figure out the f at xy. You say that the blue point will be equal to f of x, y, okay? And then you say plus, you have to figure out the slope of this curve at that point, which is just f prime at xy. You guys with me? Once you know the slope, you can evaluate this height right here by taking the slope and multiply by this width right there. คุ้นๆไหม You can extrapolate the value from the xy to something a little bit further away by taking the slope multiply by delta x. And that slope is just, okay, sorry. Slope is just the f by dx. Does that help? Okay. All right. So that's the whole idea is you take the multiplication of the slope and the distance that you want to move away from. So the slope will take care of the rest, that how high the function need to change. Okay. I take silence as an okay. Okay. All right. So come back here. What is the flux through the bottom surface? All right. I know the z component of the f sub 2 is pointing up. The surface area of the bottom surface is pointing down. So I'm going to get a negative flux. The upper portion of this one is an outflux. The bottom portion of this one is an influx. So I put a negative sign there. Bam. The value of the function at that point is just the value at x, y, z. I extrapolate along the x this much. Take the slope, multiply by the distance away from the x, y, z. I move by x, delta x over 2. I take the change along the y, slope along the y, multiply by the change along the y half of the delta y. And I'm done. That is just f sub 2 pointing in the positive z direction. And then I have to multiply by the area, but we know we already have a negative sign in the front. So I just multiply by delta x, delta y. Whoa. That is a really long calculation right here. But overall, if you look at this one, what do you see? For the whole thing, it's all reduced down to this. Of course, this cancel with this cancel with this. It has to be canceled because the only change that is going to happen here is just going to be the change along the z. And do you see what's left here for you? Yeah, very good. So what you have left to look at this one is just, actually this one already disappeared as well. So everything's just gone. The only thing left is just this term right here. That's not going anywhere. So the final result that you have left from this flux calculation is this. It's just the change of the f in the z direction with respect to z. It's a partial derivative, pretty much. Wow. and multiply by the delta x, delta y, delta z. So by doing this, you already know how to do the rest of the 4 surfaces. Yeah, you can see, but now I can try the front and the back surface. Because the front and the back is just going to be the change along the y-axis, so why not? Whatever that you're going to have left is just going to be the same delta x, delta y, delta z, and then just the change of the y component of the f along the z direction. So it's going to be partial derivative of the f in the y component with respect to y. And then you can sort of like finalize the whole thing with the leftover 2 surfaces here. Of course, these 2 surfaces will be the change along the x. So you can guess the final results will give you still delta y, delta z, delta x, and then it's just going to be the change of the x component of the function f with respect to x. Isn't that nice? And then you just have to add these 3 together. 1, 2, and 3. This summation will give you the net flux through this box right here. You see where I'm at right now? So in conclusion, the total flux out of this little box, the text is nice, they say little box right here. How much, guys? You just take 1 plus 2 plus 3. It's just 1 plus 2 plus 3. But then you can see that they have common factor of delta x, delta y, delta z. I can pull that out to the front. So it's going to be delta x, delta y, delta z. And the rest of the summation goes df sub x by dx plus df sub x by dy. Oh, sorry. It's supposed to be y. Df sub y by dy plus df sub z over z. Whoa. That is the net flux in this little box right here. Okay. Okay. Almost done, guys. Remember what we defined the divergence of the function is the net flux per volume. Can you guess what will be the final result here? Very good. I just take this whole thing, all right? And then I divide it out. Okay, I don't know where to go here. Because the volume of the box is right here. So what I can do is, there you go. Let me drag across this and then say, divide it out. Divide by the volume, delta x, delta y, delta z. So that means the term in the bracket, that is my divergence, the net flux per volume. Bam. And as we see, I don't care the size of the volume because we already made an argument earlier in this lecture that you can cut your volume down into as small as you want. So this divergence of f will be exactly there. For the super small box, you can shrink this down to 0 if you want. And that would be the divergence at that point. So do you see what this divergence of f is telling you now? It gives you the net flux within a volume. Whoa. Whoa. All right. So that's why it's now equivalent for you to speak directly in terms of the f, the vector field itself, or say, Ajan, I'm just going to keep finding the divergence of the f. And then I can pick a point and I can tell you right away around that point, what should be the net flux? What is the behavior of this vector field in terms of the flux around that point? Okay. And this actually, the conclusion is nice. At the end, the operation of this divergence is very easy. It's just a partial derivative. Even nicer, look at this, is scalar. There's no vector associated with this at all. So the divergence of f is just telling you sort of like a measure of divergenceness. I don't know. I don't think this is a word, but it tells you how plain it is, how diverse it is for this vector field at some local points. Nice. This is very nice. So to make it even cleaner, all right, so this is our last slide here, so you can relax a bit. So you can make things a little bit cleaner because you know that the final result of the divergence of the vector is a scalar. So let's borrow the scalar products and define a symbol, and that symbol we're going to name it the del symbol, the inverse delta sign. This symbol right here is in a vector format. It's an operator actually. This is a vector operator. As you can see, it's need to operate on something because it has an open, see? It's a d something by dx is waiting for something to be operated on, but it's in the vector format. So this is a vector operator. All right. So if you take this as a form of a vector operator, then the divergence of f can be written as the dot product between this del operator and the vector f. So this one is named del right here. Okay, so if you remember the dot products, I can use a bracket style. So it's a d by dx, d by dy, d by dz. That is your del operator. You dot this with the vector field, x components, y components, and z components. And everyone remembered how to do the scalar product or the dot product. You just take the same components and multiply. So it's going to be df sub x by dx plus df sub y, the y component, by dy, plus df in the z component by dz. And voila, that is your divergence of f. But you write it in a abbreviated form. It's just a del dot with the vector field vector f. Whoa. Okay, as a final conclusion right here, see, this is what it is. If you have the vector field that look like this, coming out from a point P, and then if you jump right into that point P and try to evaluate divergence of a vector at here, at this point P, you're going to get a positive number because it's an outflux. The flux is coming out from a very, very, very tiny volume in here. I don't know, does that help? So that's why this is a conclusion, the paragraph that concludes today's lecture right here. If divergence has a positive value at some point, so here they sort of like they lead you to think like a velocity field or something, yeah. So there is a net outflow in that neighborhood, somewhere around there. Okay, cool. All right, that is it for today's lecture. All right, quite heavy, I guess, because we sort of dive down into how to get to the divergence of f. I think today's lecture is more like mathematics than physics, I guess. We haven't talked about we did a little bit of Gauss's law. Okay, not too bad. โอเคหนักไปหน่อยเนาะวันนี้โอเคแต่หวังว่าพอเข้าใจอะไรได้บ้างนะหวังว่านะ Okay guys, any questions up to this point? That might have a lot of questions, yeah. I know. All right, but try to go back and do some reading a little bit more or just revise this whole thing and then things will be a little bit clearer. All right, next time I'll show you how to apply this kind of thing. Okay.